I'm all about that bass, no acid. I'm all about that bass, no acid. All about that bass, Wait, I'm gonna add some acid. Whoa.
Oh.
Whoa!
Eureka! You guys see this?
That was an awesome reaction.
Look at that.
Wow. Yeah, this is called chemistry, you guys. Have you heard of chemistry before?
We have heard of chemistry, Marisa. We actually have an affinity for chemistry, believe it or not.
We love chemistry. Gavin and I, we fancy ourselves chemists even.
You fancy yourselves? Do institutions fancy you as chemists as well?
Yeah, people would call us geochemists for sure.
Yeah. Do you have pieces of paper that say that you're official chemists?
Oh, not yet, but soon.
Maybe one day.
Well, you know what I like about things like this is that anyone can be a chemist. I'm a chemist right now, today, aren't I?
That's so true.
And even if I didn't have the goggles, I'd still be a chemist. You don't need to have all the tools and the gizmos too. It's about being curious. So we're going to be curious about chemistry today. And for all of you joining us today, watching along for this week's Rockin' pop-up, so we are going to talk about chemistry a little bit today. Maybe you can leave us a note in the comments and tell us 3 words that come to mind when you think of chemistry. Curious what comes to mind for you guys and how you feel about chemistry. Yeah, we'll see. And Gavin and Graham, can you introduce to us a little bit about the chemistry that we are going to be talking about today?
Absolutely, absolutely. So today we're talking about chemical sedimentary rocks. And so I'm going to share my screen here. And while I do, Graham, you can elaborate a little bit as well if you'd like.
Yeah, definitely. So we usually, when we think about chemistry, we think about folks with white coats and goggles, and we think about, you know, bubbling beakers and explosions and fumes. But, you know, chemistry really is going on all around us. And chemical sedimentary rocks are really kind of a beautiful way to think about that. And so, Gavin, now that you've got us onto our slides, yeah, tell us what we're gonna find out.
Definitely. And Graham, I like that you said that because you're right. Chemistry happens all around us, not just in labs, not just with people in white coats. But today we'll channel our inner mad scientist and talk about some chemical sedimentary rocks. What do you say?
That sounds great.
Okay. So I have a question for both you and Marisa and also the folks at home. Which rocks here look sedimentary to you? Go ahead, Graham. What do you think?
Well, good thing. Just 2 weeks ago, we were talking about sedimentary rocks. And what I learned about sedimentary rocks then is that they're made up out of chunks of other rocks. And so I'm looking at these and I see that one with the pen on it, that dark brown one. That one looks pretty sandy. I bet that's a sandstone, so that's probably a sedimentary rock. And then the one on the other side from there with those big brown and dark gray blocks, rounded black pebbles in there, and that sort of beige matrix around it, that looks like another sedimentary rock. And so, yeah, it's made up of those chunks of other rocks. Marisa, what are you seeing here?
Yeah, so I agree with you, Graham. Good assessment. And these other ones that aren't those 2 in the top corners, they remind me of gemstones. We talked about gemstones briefly a couple of weeks ago when we were talking about minerals. And I also just wanted to point out for everyone watching that I did add a link where you can go and look at all of our previous installments too. But yeah, these are reminding me of gemstones and minerals, which I believe we were talking about are not necessarily rocks. They make up rocks. So that makes me wonder if all of these things that we're looking at are rocks.
Well, Marisa and Graham, and everybody at home, I'm going to blow your minds here for a second. I'm going to say that every single one of these is a chemical sedimentary, or is a sedimentary rock. The ones that you pointed out, Graham, the top left and the top right, those are normal sedimentary rocks. But the other 4, these 2 and the ones on the bottom, are actually chemical sedimentary rocks. So they're made up of minerals in some cases, even though these opals. So both of these two in the middle are opals, and those aren't actually minerals because they're not formed by crystals, but they're all chemical sedimentary rocks. And so, Graham, now that we've broken the seal, we're talking about chemical sedimentary rocks. Where in the environment can we find chemical sedimentary rocks?
That's a great question, Gavin. And I see what you mean. Things that are, a sedimentary rock, we usually think, you had me tricked to thinking that the sedimentary rocks, those chunks of rocks have to be, pieces of rock that you can hold in your hand. But the trick with chemical sedimentary rocks is those are sedimentary rocks on such a finer scale. So we're going to form sedimentary rocks in places where we're not picking up chunks of rock and moving them around, but we're picking up individual atoms and molecules and moving those around. And so if we're going to form them, we need something to move those elements around. And what's a great way to move molecules and atoms around on Earth, Gavin?
Fantastic question, Graham. And you hit the nail on the head with your assessment. The way we move most atoms around on the surface of the Earth and even below the surface of the Earth is with water. And so chemical sedimentary rocks are forming from things that are dissolved in water and are redeposited as different rocks. So the places that happens are in some sedimentary layers. So here I have a schematic on the left where we have some permeable layer. So water from the surface can move through that layer. That's what it means to be permeable. And sometimes it even builds up in a saturated layer in there. And when that happens, we oftentimes get a lot of different elements or atoms that go into that water. But Graham, does it always have to be a sedimentary area, or can we get chemical sedimentary rocks associated with other places?
Yeah, so you can also get sedimentary rocks wherever you have magma. That hot water is really good at picking up those bits out of other rocks, those elements and molecules, those chemical solutions, and moving them around. So hot springs, oftentimes we see really pretty colors around those Yellowstone hot springs, and that's because those are a key place for forming chemical sedimentary rocks because they're really good at getting those stuff dissolved in water. And we'll talk about that a little bit more. And so what's one more way, and this one I kind of like because it's kind of the simplest way of how we get a chemical sedimentary rock?
Well, Graham, as you said, pretty much anywhere that we have water on the surface of the Earth, we can get a chemical sedimentary rock because water pulls constituents out of rocks and deposits them in other places. And so if we think about like a lake bed, for instance, that's where we pool a lot of water on Earth, and it doesn't necessarily look like it's filled with atoms or elements, but it is indeed filled with a bunch of atoms and elements, what we term salts. And those salts sort of get more and more concentrated as we evaporate off that lake. And so oftentimes when we get a place where we used to have a lake that totally evaporated, we will get chemical sedimentary rocks forming when you concentrate those lake waters. But Graham, how is it that we're getting those constituents from the rocks into the water? It doesn't make sense to me.
Right. Well, I think we've sort of given a good overview, and don't worry, folks, we've covered a lot of ground here. We're going to cover each one of these in detail. But, we've talked about a lot of places where we can form a chemical sedimentary rock, but I'm hungry, or maybe I'll say thirsty, to learn a little bit more about how we get these things into water in the first place.
Well, you're in luck, Graham, because this morning I had a thought when I first got up that maybe there's an experiment we can run that's analogous to what happens when water percolates rocks. So everybody watch this video of this experiment I ran this morning. Morning, everybody, and welcome to this week's edition of the Rockin' Pop-Up, live from my kitchen. So this week, as you know, we're talking about chemical sedimentary rocks, and the starting place for chemical sedimentary rocks, the easiest place to start understanding them is to understand how water from the environment gets infused with particles or constituents from rocks to make new rocks, the chemical sedimentary rocks. And so
This concept is what geologists call water-rock interaction. Simple. Water, pure water from the environment, comes in contact with rocks over a long period of time, pulls out some of those constituents, and has enough what we call salts in them to precipitate a new rock. A good analog for that is a pour over cup of coffee. In this case, I have my coffee in the top. This is the analog for the rocks. And then pure water from my kettle goes over it and makes a delicious cup of coffee, because as it contacts that coffee, the coffee grinds, it becomes infused with the constituents. Let's try it out. See, pure water comes over it, contacts the rock or the coffee, and comes out infused with some of the parts. But it's not infused with pieces of the coffee, it's just infused with parts of the coffee. Same thing with rocks. Pretty simple, right? Thanks for watching. Gotta go, my bagel's done.
Oh, Gavin, I found that super helpful. And I think something that's also, just a quick aside here to sort of, call back to what we were talking about at the beginning of today's episode, was that, little home chemistry experiments are everywhere. And every time we make a cup of coffee, we are doing a little bit of an experiment. And that, there's all sorts of ways that we find chemistry happening around us. And that just, that makes me so happy.
You're so right, Graham. It's always fun to think about a little chemistry, even when you're making your morning coffee. So we had that analog experiment, but Graham, can you just talk about the schematic here on the right, and how does this actually happen in the Earth?
Yeah. So, it's just like how you described it this morning, making your coffee. It's all about water getting into some material, whether it's rock, whether it's coffee grounds, whether it's tea leaves. And once that water's in there, it's going to react and it's going to interact with those solid materials, and it can actually take some things off of it. In the case of coffee, it's all those coffee and tea, it's all those flavorful parts of the plant that it's taking into solution, whether they're oils or salts there within them, salts and sugars in them. When in a rock, it's something very similar. Here in this diagram, you've got all sorts of these good things that you're showing with arrows coming out of this rock and into this water. You've got all these are a bunch of different elements, so calcium, silicon, oxygen, sodium, chlorine, all sorts of good stuff that's making your rock tea that you can then take somewhere and precipitate out to form a probably less delicious than your cup of coffee sedimentary rock.
I'd say it's less delicious, but intriguing. Okay, Graham. So we talked about water-rock interaction. This is how the actual waters get saturated with the stuff we need to make chemical sedimentary rocks. But let's go and talk about the environments and the places in Earth that this actually happens. What do you say?
That sounds great.
Okay. So we talked about what we think is probably the simplest area that you get chemical sedimentary rocks, and that is in evaporation, or in evaporated lake beds, say. Anywhere you get evaporation, you are getting rid of the water, and what you're left with is a more concentrated solution. So Graham, I think that we also did an experiment today in our lab to simulate this, right?
Yeah, that would be great. So start us off. So we're not going to make coffee this time, but we're going to start ourselves off with something that's going to be a little bit like a lake or a sea or a pond or something like that. You want to take it away?
That's exactly right. Yeah, I'll take it away. Let's see.
Hey folks, coming back at you now from one of the labs at UC Santa Cruz. I'm with my other gent, Graham, here. We're masked up for social distancing, and we're going to do an experiment now that shows how salts go into solution. I have some salt here. I'm going to pour it into pure water, and it's going to become dissolved. That is what we call going into solution. And then as we evaporate this water off on one of these hot plates, the salt is going to come back out of solution and is going to form a rock again. We call this precipitation. And this is how chemical sedimentary rocks form in lake beds and things like that. So let's try this experiment out. So I'm going to put a little bit of salt into the pure water, and I'm going to shake it up. It's going to go into solution. Shake, shake, shake. See that a lot of that salt is starting to dissolve now, the more I shake it. So it's basically almost gone. And now I'm going to put it on the hot plate. And as that solution dries down, the salt will precipitate out and become a rock again. Chemical sedimentary rocks.
All right, Graham. So we ran this experiment, and before we actually talk about what the results were of the experiment, I have some pictures here of places that this exact thing is happening in nature. Can you describe them?
Yeah, that'd be great. So, so this first one is a dried up lake bed, and in California we've got a great place to check one of these out. We go to Death Valley, and if we head over to Death Valley, there's all these salt beds that extend over these really long distances, or all these low areas that long ago used to hold these probably beautiful freshwater lakes. Back when the climate was a lot warmer and wetter during the last ice age. And so what happened is all those dried down, and we were just left with these salt beds across these long, flat areas. But now, Gavin, that doesn't look like a lake bed down at the bottom of the screen. That looks like a sink to me.
That's right, Graham. And you don't have to go to Death Valley to find evaporative or evaporitic chemical sedimentary rocks. If you just look at your sink and you don't wash it for a few weeks or months, you're probably going to build up some of this stuff here. This is actually called lime down here.
Mm-hmm.
And that happens because even in the pure drinking water that comes out of your faucet, there are some small amount of those constituents, those elements. Too bad it's not coffee, Graham, but those elements actually build up onto the surface of your kitchen supplies and make these layers of chemical sedimentary rocks.
Oh my gosh, another home chemistry experiment. I love it, Gavin.
That's right. But before we move on, let's look at the results of that previous experiment we did in our lab. All right, Graham, describe what we have here. So starting with this first panel.
Yeah, so as we dried this thing down, we went from that really clear water with just the, that little bit of salt dissolved in there, not really concentrated. But then as we dry it down, it starts getting cloudier. We've got something that looks a lot more like a brine, something that we know is real salty. And then down just below there, we finally get it dry enough that the salt can't fit in that solution anymore. So we start getting little bits of salt just dropping out of that solution, forming at the bottom, just those little white flakes down there. And then what happens when we take it all the way and evaporate all the water off, Gav?
Well, when we evaporate all the water off, we have some more traditional looking chemical sedimentary rocks. These are actually look kind of crystalline, and they're what we would think. They're kind of like analogous to our salt beds in Death Valley. We made salt beds, Graham.
Oh, that's so great. And, I just want to take a quick moment here to note, Marisa talked about minerals when we were talking about the sedimentary rocks. We just use classic table salt here to make this. And so we actually, in making our little salt bed, we were precipitating out a nice layer of the mineral halite. And so if you ever want to sound like a scientist at the dinner table, you can ask someone to pass you the halite.
That's right, Graham. Parlor trick that I've used many times. All right. So let's talk about some of the more traditional environments that people might think about when they think about chemical sedimentary rocks. And I feel like we have to start with geodes because folks always bring us beautiful geode specimens to look at. And so can you describe to me, Graham, where one place you would expect to find a geode or you might find a geode?
Yeah, so geodes, those are usually going to form in pockets, little pockets of space in sedimentary rocks. And so it's really important that we're in a place where there's lots of water moving through there, because those pockets can then become spaces where there's room for all those salts in the water to start precipitating out. Now, when I'm saying salts here, I mean it different than when we were talking about halite. This is a different chemistry to these salts, but we use the same word to describe them. And so, yeah, Gavin, you get some water down there, it finds a nice pocket, and then what starts to happen?
Well, Graham, the water will kind of pool into that pocket over time. And as it pools into that pocket, it sort of drops all of its constituents. All of those elements that are in there start to precipitate out over time. And what you get are these beautiful crystals along the edges of the pockets. Those are those traditional geodes. And then oftentimes, if you have a really concentrated solution, you could even fill the whole geode like this one up here on the right. But Graham, what's something that people might know of and have eaten as kids that is analogous to this process?
Yeah, so rock candy is doing something very similar. Instead of it finding a pocket in a rock, you're preparing a bowl of sugar, and when you dip your stick in there, that's kind of just like giving a space for those crystals to form, just like in the interior of that geode. And so by making rock candy, you're really just recreating, the same sort of process that forms a geode deep underground, and with a much tastier sort of mineral.
I just love all the food puns today, Graham. I'm getting hungry.
Me too.
What is a sort of special environment that this can happen, though, in the sedimentary environment?
Yeah, so, we usually think of geodes as something that you can hold in your hand or you can pick it up. But what if we have a really, really big pocket underground? Then we're going to form something that's kind of like a geode, but a little bit different, right, Gav?
You are so right, Graham. So if that little geode pocket, instead of being hand-sized, is, say, cavernous, well, we can form caves. And I think that a lot of folks who are watching will be familiar with what the interior of caves look like. You get these things hanging from the walls and growing from the bottom, and we call those stalactites if they're on the top, and stalagmites if they're growing from the bottom. And I like that you called this kind of analogous to a geode, because it is. It's basically, you have crystals growing in from every direction as you're percolating the water through the layers that are above the cave and into the top or bottom of the cave, right, Graham?
That's right. Yeah. So, not exactly the same as what's happening in the geode, but it's all about having a nice space for our water to get to and let crystals grow in that space. And, yeah, I see that you put in a picture here of some icicles, and they're actually really similar in the ways they're kind of the shapes of how these formed. The icicles look a lot like these stalactites that form from the tops of caves.
That is right, Graham. And so the sedimentary environments are sort of the more classic places you get chemical sedimentary rocks. But as we said in the beginning, you can also get them associated with hydrothermal fluids. And those are hot, salty fluids that are near magma bodies deep beneath the ground. And so, Graham, what happens and how do you get chemical sedimentary rocks from these hydrothermal fluids?
Yeah, so we're making coffee and tea again here, Gavin. You've got these hot fluids underground, right? These magma chambers are heating up the water around them. Sometimes they're baking water out of the rocks nearby them and driving water up into the rock around it. And that hot water is really good at leaching, at pulling all sorts of elements out of the rocks around it. And so any place we see a hot spring, that's a hydrothermal location. So you've got some hot rock down there that's heating up the water, and as it goes, it's picking stuff up. And so some of the things, and so, we can form stuff that's, not terribly unlike some of the stuff we've seen already, things that are like silicious, made out of a lot of silica and kind of milky white in color, things that are made out of calcite and are kind of chalky. But these hydrothermal systems, what are they really, special and kind of good at making, Gav?
Well, Graham, the thing about these hydrothermal systems is that they contact a lot of rocks. And so they get concentrated in some more rare type of minerals and constituents. And that's why if you were to ask me where I think we could find gold is always formed in these hydrothermal mineral veins. And so you get these really hot fluids that are forced up into the overlying rock above them. They are really pressurized because it's a lot of fluid in these little pore spaces. And so they break the rocks open and they make these things called veins. And these, in this middle panel is what I think of when I think of veins. You have the dark country rock or the original rock, and then these white sort of cracks in there, those are veins. And in those veins, as you said, you can get really precious metals like gold and silver and copper.
Oh, fantastic. And I'm glad that we got to bring some gold into this, right? As our state mineral here in California. It's nice to learn a little bit more about how we form gold.
Always have to talk about gold if you have the chance, Graham. And I think that there's a fourth area you would see chemical sedimentary rocks, and this is arguably maybe even the most famous, but I think that people might not even realize that it's what they're looking at, and that is concretions. Graham, can you describe how concretions form?
Yeah, so concretions form whenever you've got a part of a rock that's more porous. And so things that are often pretty porous are things like wood, bits of plants, critters, whether they're insects with their exoskeletons or whether they're bones of mammals and birds or reptiles. And so what happens when those are buried deep underground and water starts to flow through and pool in those porous spots, Gavin?
Well, Graham, when you have these really salty waters, these waters that are filled with a bunch of different elements, and they pool into the pores of those organisms, they wind up actually precipitating chemical sedimentary rocks in those spaces. And what happens is that the chemical sedimentary rocks are more resistant than the original type of material, be it bark or bone, that the organism is made out of. And so most of the time, when you find a fossil intact, that's going to be actually a chemical sedimentary rock that's replaced all of that bone in there. And the same thing with petrified wood, right?
Amazing. Yeah, that's so cool. So all along, these fossils turned out to be a chemical sedimentary rock. Oh, we've always said these things were special, but it's nice to have these reminders of just how cool they really can be.
That's exactly right, Graham. As I said, and as I've said a lot in these Rockin' pop-ups, these are my favorite types of rocks. And so I think that they're really cool and special as well. And I hope everybody out there does as well. I think that we've done a pretty thorough job of covering chemical sedimentary rocks now. And so if you're interested in joining us next week, we're going to be talking about how geologists tell time in the rock record. And so what I have here is the geologic time scale. And so geologists have a very, very specific record with specific dates that tell time in the history of the Earth. And so me and Graham are going to tell you guys how geologists find when to put those time in there. And here's a picture of a mass spectrometer. And so that's kind of a primer on what we're going to be talking about a little bit, the general gist of how geologists measure and tell time. So I hope you guys tune in next week.
Yeah. And as a little spoiler for folks, this is the stuff that Gavin and I work on as scientists. We're very interested in telling time. So we'll be very excited for next week.
That's right.
Well, I'm excited too. I think that one of the things that is most intimidating about geology for people is the kind of unrelatable time scale of things. We live our lives in terms of seconds, minutes, hours, days, and years. But when we talk about geology, we're talking about 3 to 7 million years, 9 to 10 million years, 400 million years, 4 billion years.
That's
and it
right.
kind of gets a little... So I'm very interested to hear your perspective on geologic time and the conventions. That'll be a good one. So thanks for that. And I'm glad that we dug a little bit deeper into sedimentary rocks. There are obviously a lot more to them than what we were able to cover in our previous episode. So thanks for that. And we're all still goggled up, still ready to talk about chemistry and geology and rocks. I should also say that the little experiment that we were playing with earlier is taking something that is basic, so baking soda, and something that is acidic, and I used vinegar and mixed them together, and a reaction happened. Have you guys ever played with that, Gavin and Graham?
Oh, absolutely.
Yeah, and that reaction is a classic one that I think I did when I was in elementary school to make a volcano. And little did I know then that one day I'd be studying geology. So, yeah.
Well, I think maybe you guys have some rocks you guys wanted to show off today. We didn't have any submissions yet, But just a reminder that there's a link in the description for this video that is our like Facebook event for these pop-ups. And if you want to submit a picture of a rock to be ID'd, you can just drop it there and we will go through them like next week. So any picture of a formation, a rock you have. One of the ones that I wanted to show you that I found, which I think is like kind of like a garage sale find. Is this a chemical sedimentary rock, you guys?
Oh yeah.
Oh
That's
yeah.
totally a chemical sedimentary rock.
Yeah,
Definitely.
I see the telltale signs to me of like it's kind of translucent. There's sort of some like stripage going on there, and then it's like surrounded by this more kind of more traditional looking rock material.
Mhm.
That's where I thought it was a sedimentary or chemical sedimentary rock.
Yeah. So, and you see those sort of red streaks inside of there. That's where the elements, the constituents that are in there are probably iron, and that oxidized iron is what gives it those red streaks.
Cool. Good to know.
Yeah.
I have another one that this is a sedimentary rock, but I don't think it's super chemical sedimentary. But I was just sort of I saw it earlier today and I was curious about it. I have a couple of bits of mudstone that have these interesting patterns on them. So this is just from Santa Cruz. Do you guys have anything to say about why patterns like that form?
So my guess is that those are probably little fossil bits in there. And what exactly they are, some of those look like they could be shelly bits, but my guess is that's probably like a coral that's making up a lot of that. What do you think, Gav?
Yeah, something like that. I would say it could be fossils. It could be, I don't know, bits of larger pieces of rock or concretion that is sort of more iron rich. So it's hard to tell with the beach rocks, but yeah, some sort of concretion that's iron rich that's giving it that color.
Do you guys ever notice that with the Santa Cruz mudstone that we have around here, that it does have that kind of like the variations of colors through it?
It does, not quite as pronounced as those, but there's definitely, there's some classic spots in the Santa Cruz mudstone where you can see a bit of variation. And of course, there are those, those well-known toilet bowls, as a lot of people call them, over along Westcliff, where a different, not a fossil concretion, but a concretion from probably fluids that are welling up in it when it was just starting to become a rock.
So I just had a realization. So this is a chemical sedimentary rock if these are fossils then.
Mm-hmm.
Yeah, that's right.
There we go.
That's right.
Who would have thunk it? Do you guys have anything you want to share before we
I
sign
have
off
one
for the
rock
day?
that I'll share, as long as we're talking about chemical sedimentary rocks. So, Gavin, this one will be a favorite of yours. This is a chunk of the mineral fluorite, but if you ever question how chemical sedimentary it is, and you look here, there are all this little network of sort of veins that grew across it. We call these dendritic minerals. Here, I'll get that back up for folks to see and try and let my background not get in the way. And so that's like, those are forming on the surface where the fluids are sort of sneaking through there, and they're just, tracing out these little hair thin minerals that are growing along and across it. I don't know if you want to add to that, Gavin.
Yeah, no, I think that fluorite is really cool because of that, because you can see oftentimes in the fluorite, you could see the surface as the mineral was growing. And a lot of times what that is actually inclusions of the original fluid that precipitated out the fluorite. We call these fluid inclusions, a nice aptly named thing. And so there are these little bubbles of fluid, and scientists have actually figured out how to extract those fluid inclusions from minerals and measure the original fluid that formed those minerals. So it's of scientific importance, and it's also just really, really cool.
Very nice. Awesome.
That was a good specimen. Thanks for sharing. And again, if you're watching at home, we'd like to look at your rocks too. So leave us pictures in the link that's in the description for this video. We're going to see you next week to talk about geologic time. And what's the name of that tool that we're going to be talking about?
A mass spectrometer.
Mass spectrometers. Okay, I can't wait. So thanks for joining us, guys. We'll see you next week.